Hey everyone! So normally I talk about well-known features that most experienced Prometheus users will know about. But today I thought it would be fun to talk about a few lesser-known behaviors and implementation details that most people won't know, and that just kind of do the right thing for you under the hood most of the time. I find these at least mildly interesting, and I hope you will too. And especially stick around for the last one for a little extra mystery. Okay, let's go. Factoid number 1. When Prometheus scrapes multiple targets off a scrape pool at a given scrape interval, how does it spread out the scrapes across that interval? Now, it could just naively scrape all targets at the same time, wait one scrape interval, and then scrape them all again. But that's not ideal, since that will put unnecessary load spikes both onto your Prometheus server and on your service. Now, we could just space out all targets equally over the scrape interval, but as you remove or add targets over time, the existing ones would also have to shift around to keep the even spacing. And we do want each target to have a fixed and predictable slot within the scrape interval, so that scrapes are as periodic as possible. So Prometheus tries to do a little bit better. It takes a hash of the labels and the scrape URL of each target, and then maps that hash onto the scrape interval. That makes sure that Prometheus spreads its own load more evenly, and it also prevents all instances from a service from being hammered at the same time. Now, if you have multiple HA replicas of the same Prometheus server, those replicas could still be scraping equivalent targets at the same time. So to prevent that as well, Prometheus takes a hash of its own global server labels and combines them with the individual targets hash. And since the global labels should distinguish HA replicas from each other, each HA replica then scrapes the same targets at different times within the scrape interval. On to factoid number 2. When we select time series from the TSDB in PromQL, we almost always include the metric name in the selector. The metric name describes the aspect of a system that you're measuring, like memory usage or HTTP request counts, and every series in the TSDB has a metric name. But did you know that the TSDB itself actually has no idea about the concept of a metric name? All the TSDB knows about for each series is the series label set and a stream of samples. From the point of view of the TSDB, the metric name is just stored like any other label in the special reserved double underscored name label. But the layers around the TSDB then make it look to you as if the metric name was a special thing. That's because we almost always want to refer to the metric name when selecting series, and we also want to display it in a separate way so you can spot it easily. But really, writing a metric name in front of the curly braces of a selector is just syntactic sugar, and you could as well remove the metric name in front and add a label matcher for it instead. That's also useful in case you ever need to do regular expression matching against the metric name. On to factoid number 3. Alerting rules have a for duration field that allows you to add a time tolerance before an alert starts firing. So if you write for 5M in a rule, that means that a given series needs to be consistently returned across multiple evaluation cycles for at least 5 minutes before it starts to fire. But what happens if you restart Prometheus while an alert is still pending and the for duration threshold hasn't been reached yet? Until a couple of years ago, Prometheus would simply have forgotten the for state across restarts, and so we used to recommend against using too long for durations. But by now, Prometheus tracks those for states across restarts, and since it needs to do this on a per series basis and in a way that it can efficiently look up the state of each alert series, we decided to simply reuse Prometheus's existing TSDB to track those states as well, rather than inventing a completely new database with similar needs just for this. So now, Prometheus writes the current for state for all pending alerts into a set of time series with a metric name alerts for state. The labels on the metric indicate the labels of the underlying alert series, and the value of the metric is the timestamp at which the alert series was first returned by a rule expression. So when Prometheus restarts, it can now just read this metric from its TSDB and restore the for duration tracking accordingly. On to factoid number 4. You may be familiar with the text-based scrape format of Prometheus that you can see if you go to the /metrics endpoint of an instrumented target like this. But what you may not have known is that there's no longer just one scrape format, but multiple. The original text-based scrape format is still the most common one, but it has also been used as an inspiration by the OpenMetrics project with the goal of standardizing it even outside of Prometheus. And Prometheus now supports scraping the OpenMetrics format as well. OpenMetrics looks almost exactly the same as the original text-based format with a few alterations and additions. Some client libraries, like the Go client libraries, can support it experimentally already if you explicitly turn it on, while the Java client library will even have OpenMetrics output enabled by default. The exact format is usually not something you have to worry about, and Prometheus will accept both formats by sending an accept header to the scrape target that prefers the OpenMetrics format, and otherwise it falls back to the old school text format. Note that if you want to use exemplars, for example, to jump from a metric to a related trace, only OpenMetrics supports that for now. And since the recent experimental edition of native histograms, Prometheus has even added a new protobuf-based scrape format that's currently required to transfer the native histograms, since they don't have a text format encoding yet, and it's way more efficient to transfer the many native histogram buckets using a binary format. Only the Go client library supports native histograms and that new protobuf transfer format already, but once it's stabilized, we expect to see many other client libraries to support it as well. On to fact number 5. If you sometimes have expensive PromQL queries that crash your Prometheus server with an out-of-memory exception, and you have trouble tracking down those problematic queries, then this will be useful. First, while Prometheus supports logging all completed queries to a log file, that won't help you find queries that were still running while Prometheus crashed. And ironically, those queries are exactly the ones you want to track down, since they likely caused the crash to begin with. So to help you with this, Prometheus also keeps track of all currently running queries in a special memory mapped file in its TSDB data directory. That file is named queries.active, and it contains a JSON-like representation of all currently active queries. The main purpose of that file is not for you to go and look into it manually, but if Prometheus crashes while executing some queries, those queries will be left over in the file and will be detected by Prometheus when it starts up again. So when Prometheus sees any queries in that file up on startup, it will just log a warning that lists all of those queries, and that way you can figure out which queries were causing the problem. Let's get to fact number 6. In my recent video about data selection in PromQL, I mentioned that Prometheus explicitly marks some series as stale in certain situations, like if a series disappears between two scrapes of the same target, or if an entire target disappears, and so on. Instant vector selectors can then immediately omit those series from their output if the series have been marked stale. But how do staleness markers actually work in the TSDB? For each series, the TSDB itself only knows about the series label set and the associated samples. But each sample value is a 64-bit floating point number, and it turns out that we can use some quirks of the floating point standard to encode staleness markers as a regular sample value with a specific bit pattern without causing any collisions with other possible values. You may already know that floating point numbers support special values like infinity or negative infinity, and also a special NaN or not a number value. Usually you will see NaNs as the result of operations with a mathematically undefined result, like dividing 0 by 0, subtracting infinity from infinity, or in Prometheus for a quantile time series of a summary metric that hasn't received any observations yet. So there are definitely some valid use cases where we want to directly return an NaN sample to the user, so we can't just use a normal NaN as a staleness marker. Now the interesting bit is that the floating point standard actually defines not just a single NaN value, but many. There are two different overall types of NaN, and then within those two types, there are also many bitwise variations. First of all, an NaN is any number that has all the exponent bits set to 1 and the fraction set to anything other than 0. And then within that, there are so-called quiet NaNs that have a 1 as the most significant bit in the fraction part, and signaling NaNs that start with a 0 in the fraction. And in Prometheus, we chose to use a specific signaling NaN with a 2 in the fraction to encode a staleness marker sample value. And then PromQL and all the relevant code layers around the TSDB recognize and interpret those special NaNs as staleness markers and handle them appropriately in instant vector selectors. And since a normal NaN will have a different bit pattern from a staleness marker NaN, you can still use those normal ones without any issues. Alright, on to the seventh and last item, which is one that almost nobody in the world even knows about. And even now, I won't actually say too much about it, except that I can neither confirm nor deny whether there are any Easter eggs either in the Prometheus server or in any of the other components of Prometheus. Again, I won't spoil anything, but who knows, maybe one day one of you will stumble over something. And in case you do, let me know in the comments below the video, but please don't include any spoilers. Alright, so these were 7 interesting tidbits about Prometheus that I hope you found at least mildly interesting or even useful. Let me know down below how many of these you actually knew about already, or if there were others that you would have liked to see. And if you want to learn Prometheus from the ground up in a structured way, please check out my trainings at training.promlabs.com. See you in the next one.